Okay, thank you very much. So good morning or good afternoon, everybody. It's 4 a.m. in the morning here in Edmonton. So please bear with me if I am not very well. Today I'm going to talk about the cyber physical system approach to zero defect manufacturing and the light gauge steel frame assemblies. This is a work done by one of my postdoc who's now moved to a senior lecturer position at the Northumbria University. So from Dr. Pablo Martinez, and it's in collaboration with Dr. Mohammad Al Hussein, who's here in the Department of Civil Engineering at the University of Alberta as well. So the reason we are talking about steel frame assemblies today is evident from where we come from. Edmonton is located in the very far end of the world, in nowhere. So it's quite far in an area where the temperature can go to -40, -45 degrees quite easily, mostly in January and February. So you can see that the temperatures around us are quite extreme. So that's why most of the houses built over here are either steel framed or they are wood based manufacturing. So that's why at the Department of Mechanical Engineering, we are focusing on those areas most importantly. So here at the university, I'm currently running two labs. One is the Laboratory of Intelligent Manufacturing Design and Automation. That's what you will see. And the second one is the Aquaponics 4.0 Learning Factory, which is also connected to these projects, but a little bit different. And Dr. Pablo Martinez is now currently residing at the Northumbria University. So as I mentioned, here in Canada, steel framing and also modular offsite construction is quite important because most of the houses we build, we don't have that kind of temperature that we go outside in the 12 months of the year and build structures. So usually the winter lasts at least 6 to 7 months of the year. So that's why it's pretty cold. So most of the construction companies, they try to build modular offsite kind of manufacturing. The reason is that they can have more controlled environment within the facility, and they can develop these modules of different types of houses or parts of the houses, and that they can bring it to the real sites when the temperature or the environment permits that. So if you look into the modular construction on the top, and you can see the side build construction, when you are moving to a modular kind of structure, you're actually also getting a lot of time saving. That could be from 30 to 50% of the time saving when you build activities in parallel. So you can do most of the building construction within the facility, and then you bring those modules and you can do it. And there are many examples across the world on these kind of modular offsite constructions. One of the recent example is a hospital built in China. When a COVID hit, there was one hospital which was built in 10 days. The reason is that this kind of technology is getting more and more popular is for those kind of devastating situations when you have to go and build things internally and then just bring those modules outside. So what we are interested in is in design and engineering of steel frame, which you can see on the picture left. So what you do is initially you design and engineer those based on different types of parameters, a lot of data coming from architecture, from BIM modeling. So you model those data in a CAD environment, and then you send that to a manufacturing station which manufactured those steel frame, and then you send it and through the transportation and installation. Here at the University of Alberta, we have this kind of facility, the manufacturing machine, which you see in the middle. We have developed that machine ourselves, and we have that possibility to do all the steel framing there. We also build the wood framing stations there. So mostly this paper will be talking about that kind of manufacturing process and how this machine can be optimized based on the cyber physical system. And then you can then do the transportation side. So I'm not focusing on the design engineering and also transportation, but mostly on this kind of machines, which we have a lot outside here in industry in Alberta. So when it comes to offsite construction, prefabrication, they improve the quality of the construction. Yeah, and you can see that the poor quality can cost between 8 to 21% of the overall process, right? So it's a quite important aspect which you will need to handle. So quality in those kind of offsite construction, which you need to do, it's a very similar like a manufacturing process. And if you look into the prefab New Zealand report, it gives you some indications on the rework ratios, which is around 68% for these kind of processes. And when you look into overhead costs due to quality issues, it's 8 to 12%. And when you look into quality issues due to manufacturing defects, that is 20%. So these are big numbers. When you look into these numbers, you really want to kind of create an impact by optimizing these processes. So quality should be a selling point for the offsite construction. However, quality control is manual, mostly paper-based and error-prone. So that's why we need to look into how to automate these processes. That's what we are doing. And no continuous quality control during the manufacturing process exists currently when it comes to steel framing processes. So what we are trying to do is to create a quality station, post quality station, and also real-time quality monitoring within the manufacturing process. So this also gives you another indication which state that when it comes to steel framing, where is the steel framing more important, especially the assembly process of these steel framing. So when it comes to the architect, they might be more interested in that. The GCs, CMs are more interested in that, but usually when it comes to the manufacturing process itself, people don't care a lot about these steel frames. They just want to manufacture them, but they don't care a lot about how they are installed, how they are manufactured, what are their particular processes. So this is kind of also an important indication that we have to look into this a bit further. Now let's talk about what this machine contains. So if you look into this machine, you provide these steel studs into this machine, and then you have this fastening area where you have multiple guns, depending on what your processes are, that you're cutting these steels or you're providing screwing process. What we are doing in this particular paper is looking into the screwing process, at how effectively we can screw, and then also to increase the life of tool based on the ZDM technology, ZDM methodology, and also the cyber physical system. So this is this fastening area, which you can see that there is a overhead gantry system which moves around, and it actually do the assembly process when these studs are coming to that station. And we are looking into cameras through the cameras to identify where the machining processes is happening. So that's kind of the overall structure. Now, what is ZDM? ZDM is a zero defect manufacturing concept, which is very popular when it comes to lean techniques. And then what it does is that you take the machine, you actually look into inspecting the equipment, and then looking into the data analysis coming from that inspection process, and then you can define your preventive maintenance based on that. But you can also do the same thing with the product. You can identify if there is any inspection needed on a product, and based on that, you define your product quality, and then that product quality data analysis can tell you when the repair need to be done on the system or on the product. So this kind of a continuous closed loop system, which looks into monitoring the health of the machine, but the health of the product at the same time. And with the work collaboratively, that creates a zero defect manufacturing system, which is important. So what we did is we just take that concept of zero defect manufacturing, we created our own cyber physical system based on that architecture. Cyber physical system looks into both sides. So if you see the top side, that is the process oriented cyber physical system, and on the bottom you can see that is product oriented cyber physical system. So I'll go one step one by one step, and you can see where things are happening. So the very first thing is that you need to look into inspection process in the middle. That inspection process is either for the product or for the machine. So starting with this in the middle, and then you're moving towards synchronizing the data, which your event handler will take that data, and you kind of start by looking into what kind of inspections are there based on the camera information which you can have. Then you store and analyze the data in your big data storage system, which we are currently using as an ontology models, and then build your predictive models based on that, then transform the data to check product and process statuses, then correlate their data and communicate their data to support the decision process on the right side. So you take that decision process based on whatever the quality is, if you rework need to be done or if anything else need to be done. So you take that decision, and then the user receive that input and use data for continuous improvement in the future. So you can store that data and use it for the future system. So this kind of the overall architecture of what we developed both for the process and for the product. Then the next step was to then apply that on a particular case study where we took this screwing process as one of the case study. So the case study was done in about 9 hours, where we took around 7,585 operations based on this screw fastening operations, and we looked into the health of the machine and the product and see what is happening and if there is any correlation between some of these KPIs. So the KPIs are listed here in the table, and the important KPIs over here is the PQ, which is the counts the number of the screw fastening operations performed, and then RQ, which is the counts the number of rework screw fastening. And based on these two KPIs, we are able to calculate our RRT and TRR. RRT is the rework ratio per tool that resets after a tool change has been reported. And then the second one is the total rework ratio. So you can actually look into how many reworks you need to do once a product, once you're manufacturing a product and you realize that after some time a product is not fastened correctly. So then you have to do a rework, and that goes back to the operator. So we looked into some of these ratios, and then we wanted to see what are the correlation between these based on the cyber physical system. So the way it works is that you have these studs, your system, your camera system, they can detect if your connection, so once the manufacturing is done on the machine, if the correction is pass or fail, and that is based on the angles which you are actually looking into. So the angles between these studs should be 90 degree. Usually there is a little bit of tolerance. So 90.28, for example, could be a stud which would be correct, and that will pass. And the inspection process here is the good screw. So the status of the system will give you a pass. But sometimes it might be possible that your angle might not be the right one, that is 93.74, and that can fail. So then you'll have to look into if your system will be pass or fail based on the angle information which we are getting from the camera between the stations. Then also you can actually look into some other data for a tool life of 37 minutes and 20 seconds. You can see that the total rework ratio was 6.8%, and the current rework ratio was around 4.4%. So it's kind of some the thing which we got directly from these experiments which we conducted. And you can also see here a bit more details on the relationship between the product and the machine health. So you can see from these tables that there is a one-to-one correspondence or relationship between RRT's TTR, which is the total total rework ratio, and current rework ratio for this system, and then also the tool life of the product. And you will probably see that much easily over here, that you have the tool life starts over here. For example, this is just an example where the tool life starts, and then there is a point where you need to replace your tool, and then it goes to the next one, and then the tool life restarts again. There is a continuous relationship between the rework ratio per tool, and you can see over here from that, and these are the total rework ratios which we can expect from the process. So based on these information, we were able to kind of identify the relationship between these KPIs, but also we were able to kind of identify where the forecast tool change need to happen. So based on the tool life, we were able to identify when is the best time to change your tool when it comes to scenarios like these, and an optimal time for your tool change. So that's kind of the goal of this paper. So in conclusion, future manufacturing processes and smart factories will rely on real-time production system. So that's why system like these based on cyber physical system is extremely important. That can provide you really good data-driven zero defect manufacturing strategies. So by focusing on the existing inspection method, the manufacturing process is monitored, focusing on product quality and machine health while supporting the operator decision making in terms of the rework and preventive maintenance. So it's not only providing you this relationship between reworks and the tool life, but it also triggers when the next preventive maintenance need to happen for the operator based on this kind of ZDM cyber physical system. So a forecasting model between rework ratio and the tool life is briefly discussed in the preventive tool change are shown to reduce between 2% and 3% the amount of rework required due to the defective screw fastening operation in this kind of processes. So that's all for today. In the future, we will be extending this kind of study into including more KPIs and seeing the impact of each KPI in each other. And we are also publishing on the inspection itself based on machine learning algorithms, and also looking into the digital twin ideas for the same kind of system. So that's all for me. If there's any question, I'm open.
Thank you very much for your nice presentation. There is any question for the audience?